Here's something remarkable about American home energy consumption. A device costing $25 can reduce annual heating and cooling bills by approximately $180 in typical homes. The device takes about 30 minutes to install. The operational requirement after installation is essentially zero. No behavior changes, no maintenance, no learning curve. The device does all the work automatically, continuously, forever. And yet approximately 40% of American homes still operate with manual thermostats that don't provide these savings. The disconnect between available technology and actual adoption represents one of the stranger patterns in residential energy efficiency. Programmable thermostats have been widely available for over 40 years. The energy savings are well documented, consistent, and substantial. The payback period runs under 2 months in most climates. Yet millions of homes continue using manual thermostats that waste hundreds of dollars annually. Understanding how programmable thermostats actually save money, why they work so consistently, and what specific steps optimize their benefits can help American homeowners capture savings that are essentially waiting to be collected. The basic principle underlying programmable thermostat savings is automated setback. Heating and cooling systems consume energy proportional to the temperature difference they maintain between indoor and outdoor conditions. Reducing heating set points during periods when the home is unoccupied or when occupants are sleeping substantially reduces energy consumption during those periods. The same principle applies to cooling set points, though with inverted direction. A home heated to 70 degrees during occupied periods but allowed to drop to 62 degrees during sleep and work hours consumes 15 to 25% less heating energy than one maintained continuously at 70 degrees. The equivalent cooling savings run similar magnitudes. The implementation through programmable thermostats automates these setback patterns that humans would otherwise need to manage manually. The thermostat maintains occupied set points during hours when occupants typically need comfortable temperatures. It automatically drops set points during hours when occupants are sleeping, at work, or otherwise don't need full comfort. The automation eliminates the friction and forgetfulness that prevent most homeowners from managing manual setbacks consistently, producing the full theoretical savings rather than the partial savings that intermittent manual management produces. Derek Hollingsworth, a utility energy efficiency specialist in Ohio who has analyzed thousands of residential meter datasets comparing programmable and manual thermostat installations, has documented consistent savings patterns across his studies. His comparative analysis of 2,340 homes shows average annual savings of $156 to $220 for homes with properly programmed thermostats versus equivalent homes with manual thermostats. The savings vary with local energy prices, climate severity, and specific occupancy patterns, but remain substantial across virtually all American climate zones and usage patterns. The history of programmable thermostats traces back to early electromechanical, timer-based controls developed in the 1970s. The original technology used mechanical clocks connected to temperature set point mechanisms to achieve automated setback. The reliability issues and programming complexity of early units limited adoption substantially. Electronic controls developed in the 1980s improved reliability and simplified programming, accelerating adoption. Digital programmable controls in the 1990s added substantial flexibility. Smart thermostats with Wi-Fi connectivity and learning algorithms have extended capabilities further in recent decades. The technology continues evolving, with each generation typically offering improved capabilities at reduced cost. The smart thermostat category developed in the 2010s represents the current state of the art. These devices add learning algorithms that adapt to occupant patterns, smartphone control for remote adjustment, integration with home automation systems, detailed energy consumption reporting, and various other advanced features. The incremental savings beyond properly programmed, conventional programmable thermostats typically run 5 to 15% in documented studies. The full-featured smart thermostats cost $200 to $300 compared to $25 to $50 for simple programmable units, producing longer payback periods but additional capabilities that some homeowners value. Constance Wheaton, a building science consultant who has performed programmable thermostat installations in over 600 homes as part of utility energy efficiency programs, has documented the practical considerations that affect actual savings achievement. Her experience shows that a $25 basic programmable thermostat with proper programming typically achieves 90 to 95% of the savings that an advanced smart thermostat captures. The remaining 5 to 10% comes from smart features like learning algorithms and precise scheduling. Most homeowners achieve substantial savings with modest investment, without requiring expensive advanced equipment. The programming approach for optimizing savings involves understanding the specific patterns of occupancy and comfort needs in each home. Weekday morning warm-up from nighttime setback should begin approximately 30 to 45 minutes before occupants typically wake. Daytime setback can begin approximately 30 minutes before occupants typically leave for work. Evening warm-up from daytime setback should begin approximately 30 minutes before occupants typically return home. Overnight setback can begin at typical bedtime. Weekend programs may use different schedules reflecting different occupancy patterns. Careful attention to these timing details optimizes both comfort and savings outcomes. The magnitude of setback that optimizes savings without comfort issues typically runs 6 to 10 degrees in most homes. Deeper setbacks produce marginally greater theoretical savings, but introduce potential comfort issues during warm-up periods, and may require heating equipment to work longer recovering from deep setbacks. The specific optimal setback depth depends on home characteristics including thermal mass, envelope performance, and heating equipment sizing. Starting with modest 6 to 8 degree setbacks and adjusting based on experience produces good results in most situations. Roland Kleinfeld, an HVAC contractor in Minnesota who specializes in residential heating system optimization, has documented a common misconception that affects programmable thermostat use. Many homeowners believe that leaving thermostats at constant temperatures saves energy because heating systems use energy recovering from setback periods. This belief is physically incorrect. Heating systems must replace heat losses through the building envelope that occur continuously during occupied periods but reduce substantially during setback periods. The reduced losses during setback more than offset any recovery period energy consumption, producing net savings as the physics and documented measurements consistently confirm. The seasonal programming considerations affect how programmable thermostats should be operated throughout the year. Heating season programming focuses on overnight and daytime setbacks with warm-up periods for occupied hours. Cooling season programming focuses on daytime warmbacks when homes are unoccupied with cool-down periods before evening occupancy. Shoulder season programming may use different patterns reflecting modified comfort needs and ambient conditions. Many programmable thermostats allow multiple program schedules that can be selected to match seasonal patterns, though some require manual program updates as seasons change. The humidity and recovery time considerations affect proper programming in certain climates. Humid climates may require longer recovery periods from cooling setback, since air conditioning removes moisture from air in addition to cooling, with dehumidification requiring substantial time. Winter recovery from deep heating setbacks in very cold climates may require longer warm-up periods than initial estimates suggest. Observing actual system performance during the first several weeks after installation allows fine-tuning of program timing to optimize outcomes for specific home and climate conditions. Emily Rasmussen, an environmental scientist who has studied household energy consumption patterns extensively, has documented how programmable thermostat benefits vary substantially based on household occupancy patterns. Single-person households where the occupant leaves for work daily achieve the maximum theoretical savings from automated setbacks since the home is unoccupied for substantial daytime hours. Multi-generation households with varying schedules achieve somewhat reduced but still substantial savings. Retired households with irregular occupancy patterns achieve smaller savings since homes remain occupied more consistently, though still meaningful savings through sleep period setbacks. Understanding specific household patterns enables optimal programming for each situation. The integration with other energy efficiency measures compounds savings substantially. Homes with improved insulation and air sealing achieve greater programmable thermostat benefits, since the reduced heat losses during setback periods represent larger percentage savings. Homes with properly sized heating equipment recover from setbacks more efficiently than homes with oversized equipment. Homes with zoned heating and cooling can apply programmable setbacks by zone, matching setbacks to actual occupancy patterns in different areas. The combination of programmable controls with other efficiency improvements produces compounding benefits beyond what any individual measure produces alone. Now for the obstacles and limitations that affect programmable thermostat applications. First, the programming complexity deters some homeowners from utilizing full capabilities. Despite efforts to simplify user interfaces, many programmable thermostats present programming tasks that homeowners find intimidating or confusing. The result is devices installed but never properly programmed, capturing zero savings despite the capability to save hundreds of dollars annually. Utility company energy efficiency programs often include free installation and programming services specifically because the programming step creates barriers for many homeowners. Second, the compatibility considerations limit options for some heating systems. Traditional low-voltage control circuits accommodate nearly all programmable thermostats without issue. Heat pumps with electric resistance backup heating require thermostats specifically designed for this configuration to prevent expensive electric backup operation during setback recovery. Some hydronic heating systems use 24-volt or 120-volt control circuits incompatible with standard thermostats. Evaluating compatibility before purchase prevents frustration from incompatible equipment. Third, the installation challenges for certain situations exceed typical homeowner comfort levels. Thermostat wiring sometimes runs only 2 or 3 wires in older installations that modern programmable thermostats cannot accommodate without additional wiring. Common wire requirements for smart thermostats with Wi-Fi functionality create installation complications for many existing systems. Transformer sizing issues can affect operation in some older installations. Homeowners uncertain about their installation should consult HVAC contractors before attempting self-installation to avoid potentially damaging equipment or system malfunction. Fourth, the safety considerations for hot water heating systems require attention during programming. Freeze protection becomes important in homes with hydronic heating and winter setback schedules. Setting nighttime set points too low in very cold climates could theoretically allow interior temperatures to drop to levels where pipes risk freezing in poorly insulated sections. Maintaining minimum setback temperatures of 55 to 60 degrees addresses this concern in virtually all situations while still producing meaningful savings. Fifth, the lifestyle flexibility limitations affect programming effectiveness in irregular households. Homes with frequent schedule changes, guests with different comfort needs, or unusual occupancy patterns may struggle to optimize savings through rigid programming. Smart thermostats with manual override capabilities and learning algorithms address these limitations more effectively than conventional programmable units. Homeowners with highly variable lifestyles may find smart thermostat features worth the additional cost despite the longer payback period. Despite these considerations, programmable thermostats represent one of the highest return on investment improvements available for virtually all American homes. The combination of low cost, simple installation, automatic operation, and substantial ongoing savings produces extraordinary value propositions that few other improvements can match. The environmental implications of widespread programmable thermostat adoption extend beyond individual homeowner economics. If the approximately 40% of American homes without programmable thermostats installed and program them properly, national heating and cooling energy consumption would decrease by approximately 2 to 3%. The corresponding reductions in carbon emissions, power plant operation, and associated environmental impacts would be substantial. Various utility programs, government incentives, and private sector initiatives promote adoption recognizing these broader benefits beyond individual homeowner savings. The long-term trend toward increasingly sophisticated control systems suggests continued improvement in potential savings. Predictive algorithms that anticipate occupancy patterns from historical data refine scheduling optimization. Integration with home automation systems allows coordinated operation with lighting, ventilation, and other systems. Integration with utility time-of-use pricing structures can shift consumption to lower-cost hours. Integration with solar generation can shift consumption to peak production periods. The continuing evolution suggests that current programmable thermostats represent an important step, but not the endpoint of heating and cooling control advancement. Trevor Ashcroft, a smart home integration specialist who has installed advanced thermostat systems in 85 homes integrated with comprehensive home automation, has documented performance patterns for the most sophisticated implementations. His measurement shows additional savings of 10 to 25% beyond conventional programmable thermostats in homes with sophisticated integrations. The additional savings come from predictive occupancy detection, coordination with other home systems, and response to time-of-use pricing when available. These implementations represent the high end of what's currently achievable through control optimization, though the additional complexity and cost exceed what most homeowners require. The insurance and property value implications of programmable thermostat installation receive minor attention in home valuation but do affect buyer perceptions. Home buyers increasingly expect programmable or smart thermostat installation as a baseline feature. Homes without these features sometimes receive minor value discounts reflecting buyer expectations. Homes with well-integrated smart thermostat systems may receive small value premiums, though the magnitude typically doesn't justify installation solely for resale value considerations. The customization options for programmable thermostats allow matching specific household needs beyond generic weekday-weekend programming. Homes with shift workers can create programs matching their specific schedules. Vacation programs can maintain minimum temperatures during extended absences. Multiple set-point programs can accommodate different occupancy patterns during different seasons or life situations. The flexibility to customize programming produces better outcomes than one-size-fits-all approaches could achieve. The research at Oak Ridge National Laboratory on residential thermostat performance has generated important findings about actual savings versus theoretical savings. Their long-term monitoring studies tracked actual energy consumption before and after programmable thermostat installations across hundreds of homes. The documented savings averaged 11% for heating energy and 9% for cooling energy, translating to dollar savings of $140 to $280 annually, depending on home size, climate, and energy prices. The consistency of savings across diverse homes and climate conditions provides strong evidence that programmable thermostat benefits are real, measurable, and replicable across broad ranges of applications. The particular importance of proper programming cannot be overstated, since improperly programmed thermostats capture essentially none of the available savings. Research has documented that approximately 30% of homes with programmable thermostats installed never have them properly programmed, either operating in hold mode with constant set points or with programs that don't match actual occupancy patterns. These homes pay for the thermostat hardware but capture none of the energy savings that drove the purchase decision. The programming step represents the most important action for realizing benefits, and should not be skipped despite the modest complexity involved. The warranty and reliability considerations for programmable thermostats typically prove excellent for quality products. Major manufacturers offer warranty periods of 2 to 5 years on programmable thermostats, with failure rates in the low single digits across warranty periods. The electronic components have proven reliable across normal residential operating conditions. Most thermostats continue functioning well beyond warranty periods, with typical useful lives of 10 to 20 years before replacement becomes desirable either for functional failure or to access upgraded features in newer models. The aesthetic considerations for thermostat selection receive more attention than they probably deserve from a pure energy savings perspective. Various manufacturers offer thermostats ranging from simple utilitarian designs to elaborate touchscreen interfaces with custom backgrounds and architectural-looking finishes. The aesthetic choices don't affect energy savings, which depend entirely on programming rather than appearance. Homeowners can select models matching their aesthetic preferences without compromising savings potential, though the simple models typically offer better value per dollar for pure savings-focused installations. Melanie Ashford, a homeowner advocate in Tennessee who has conducted outreach to hundreds of families about energy efficiency opportunities, has documented the adoption barriers that prevent programmable thermostat installation despite clear benefits. Her surveys identify fear of complexity, concerns about initial investment, belief that savings wouldn't justify the effort, and simple inertia as the primary factors preventing adoption. Addressing these barriers through education, simplified installation services, and clear communication about actual benefits produces higher adoption rates than purely technical approaches achieve. The barriers are largely perceptual rather than practical, suggesting that information access matters more than technology development for expanding adoption. The installation process itself takes most homeowners 20 to 45 minutes for straightforward replacements. The steps include turning off power to the HVAC system. At the breaker, removing the existing thermostat from the wall, labeling the wire connections, mounting the new thermostat base plate, Connecting the wires to corresponding terminals on the new device, attaching the faceplate, restoring power, and running through initial programming setup. Most modern thermostats include clear written instructions, online video tutorials, and telephone support for questions that arise during installation. The combination of straightforward installation steps with comprehensive support resources makes self-installation practical for most homeowners regardless of prior HVAC experience. The utility rebate programs in many regions further improve the economics of programmable thermostat installation. Various utilities offer rebates of $25 to $100 for qualifying thermostat installations, effectively covering the full cost of basic models or substantially reducing costs for advanced models. Some utilities provide free thermostat installations for qualifying customers, particularly those enrolled in income-qualified energy efficiency programs. Investigating available rebates before purchase can reduce out-of-pocket costs to essentially zero for many homeowners while still capturing the full operational savings. The combination of rebate programs with ongoing energy savings produces some of the most favorable payback periods available in residential energy efficiency improvements. Consider what properly programmed thermostats mean for a typical American family currently using manual thermostat control. A $25 investment and 30 minutes of programming produce $150 to $250 in annual savings continuing indefinitely. The total time investment is essentially one evening, including programming time and learning basic operation. The savings accumulate month after month and year after year without any additional effort, maintenance, or adjustment. The comfort actually improves because warm-up periods produce comfortable temperatures before occupants arrive rather than requiring them to endure cool or warm homes while equipment catches up. The environmental benefits include reduced carbon emissions, reduced power plant operation, and reduced resource consumption. The investment payback runs essentially immediate, with first-year savings typically exceeding purchase and installation costs by 5 to 10 times. The approach works across virtually all American homes with conventional heating and cooling systems. The skills required are basic and accessible to most homeowners willing to read simple instructions. The tools required are essentially nothing beyond a screwdriver. The opportunity exists for millions of American homes currently operating without this basic efficiency improvement. The combination of low-cost, simple installation, automatic operation, and substantial savings creates an opportunity that few other improvements can match. The question for homeowners currently without programmable thermostats isn't whether to install one. The question is why that installation hasn't already happened. The answers typically involve inertia, underestimated benefits, or perceived complexity that doesn't match reality. For the vast majority of American homeowners still using manual thermostats, installation of a basic programmable unit represents perhaps the highest return on investment home improvement available. The savings continue for decades with zero ongoing effort. The comfort improvements begin immediately. The environmental benefits accumulate continuously. The opportunity essentially costs nothing, in meaningful terms while producing lifetime benefits that few other actions can approach.